Good morning. Okay, so let's finish this Lagrange multiplier. So basically the constraint problem, and then we're gonna get on to the new topic, double integral. Okay. Yeah. So in previous lecture we were talking about the constraint problem. The objective here is to minimize or maximize function f. At the same time, it's a subject to a constraint a function g x y equal to c. Okay, so we're going to restrict ourselves to a simple case, just a plain function of two variables. All right? Yeah. Okay. So in this case here, we in the previous lecture, what we figured out is the constraint basically means you're walking along this curve in the xy plane, which is this curve here, and at this mean and max location on the surface, okay, on that function fxy there, when you're walking along here, at the location, at the critical point, we have this relationship. So at the critical point, the gradient of this function f is parallel to the gradient of the function g. Okay, so that's a critical at the critical point, and this condition at here means del f meaning df over x equal to this. So this function meaning this one here. So the two sides equal to each other, meaning you have a partial fx equal to negative lambda multiplied by this, and this partial f over y equal to negative lambda multiplied by this, right? Yeah, so that gives us two equations. Okay, so that gives us these two equations here. So two equations, and the lambda is a constant, certain constant here. And we can use the third equation, which is a constraint at here. So basically, with these three equations that are here, right, 1, 2, 3, and we'll be able to figure out, okay, the x, y, and the lambda value. Okay, so that's this kind of constraint problem here. So we'll be able to figure out x, y, and lambda. So you probably don't really care about the lambda value, right? You care about this xy value because xy gave you this critical points, right? So the xy value, based on the xy value, then plug the xy value back into this objective function right here, and you can get this so-called, whether it's a mean or max point. Okay? Yeah. Now, I did mention one thing is, these three equations in here, right? These three equations here, you can solve these three equations, that's absolutely fine. Or the other way is particularly useful when you have a function of more than two variables, and also when you have a function maybe more than one constraint. Maybe you might have a couple or even three constraints, more than that. So what we do is we can define ourselves a w, which is fxy plus lambda gxy minus c. We can define ourselves a w here, and we can see that when you let this del w equal to 0, that give exactly the three equations added here. Okay, so that's the this function here. We call it Hamiltonian function. Okay, but the names doesn't matter. But you need to know that the lambda here is what we call the Lagrange multiplier. Okay. So lambda is so-called Lagrange multiplier. So del W equal to 0 will give you exactly the three equations. Okay, exactly three equations. Okay. So when you solve this kind of constraint problem, you don't necessarily have to write this separately here, but you need to write down these three equations first in order to solve. Right? Yeah. So let's take a look at examples. Okay. Yeah. So I'll use one example right here and to show you the typical procedures of solving this kind of a constraint problem. And that basically, you can use that to for one of the assignments. So example is to find the minimum value. Find a minimum value, or maybe values, we don't know, okay, for fxy, okay, equal to this. Okay, so this is the surface function here, subject to constraint xy equal to 3. Okay, so this is an example here. So maybe I'll draw it, okay, just illustrate what this. So if I draw it out, okay, so first we can draw this x squared plus y squared, and that's a paraboloid. Okay, so that's a paraboloid. Yeah. And then we can draw this xy equal to 3. So xy equal to 3, that's in the xy plane, right? In this xy plane. And this is a parabola, right? It's a parabola here. So if you recall that, this guy here basically, in xy, if you look at an xy plane like this, it's like this, right? It's like this, right? Yeah. So if I draw it over here in the 3D, so it's going to be, you know, one is over here, and the other one is on the other side, right? On the other side there, okay? Yeah. So I'll just draw one here. Okay, so now the whole question is basically you're walking along this line in here, or this curve, and you're trying to find the corresponding minimum value, on this surface here while you're walking, right? Yeah. So you can imagine when you're walking, it doesn't matter which way you're walking, okay? When you're walking and there's another guy on the top of this here, which is on the surface, right? So when you're going here, and then this guy will trace out a certain kind of a curve on that surface. Okay? Yeah. So apparently, you probably wonder, why is it going to be a minimum value we're trying to find? Why is it not going to be a maximum? This is actually, you can visualize, you can imagine that, right? While you're walking here, and the curve traced out on that surface will definitely give you a minimum somewhere over here. That makes sense, right? Yeah. So as a matter of fact, if you look at this question here, before you start to solve, so how many minimum values do you think you will find? Only one? Remember this curve here, right? This curve, this curve, one is over here, the other over here. There are two parts of the curve here. So if you're walking along here, you find one. If you walk along the other one, which is basically on the other side there, right? On the other side there. So you should find another one. So actually, you're going to find two minimum values. Okay? Yeah. Okay. So we're going to make use of three equations that are here, okay, to find our minimums. So first, three equations. So before we put down the three equations, maybe let's put down what df over dx is, right? df over dx is 2x I hat 2y g hat. And dg over, no, sorry, I'm talking about here. Del f, del g. Okay, so del f, del g. So del f is this, del g, okay, so del g, so in this case here, my gxy, is xy equal to 3, right? Yeah. So in some textbook, you can see, some people maybe define it as gxy equals xy minus 3. But actually it's the same thing, okay? It's the same thing. When you're taking breeding vector, breeding of this g function, if there's a constant, the constant doesn't play any roles. So in this case, my del g will be y I hat plus xj hat. Okay. So then I'm gonna make use of this equation set here, the three equations. Okay, so to form my equations. So first equation is this 2x equal to negative lambda multiplied by y. So I'm gonna move everything into one side. Okay, so 2x plus lambda equal to y. 2y plus lambda x equal to 0. And then the last one is constrained, xy equal to 3. That's a 3. So, okay, so these are the three equations we obtained based on that conditions. Okay, so constraint, and these two here is what's going to, based on the condition of the critical points. Okay, so then, now the typical procedure here is this. The first step is this is, well, I give you a step here, but this is not the only way of doing it, okay? Yeah, but usually you can, usually it works. Yeah. Is everything all right? Yeah. Okay. Okay, so now step number one is basically to express what you want to express lambda in terms of x and y. Okay, express lambda in terms of x, y. So your lambda only appears in the first two equations. So you can find this expression for lambda using either the first one or the second one. Okay? So I'm going to use the first one here to find the expression for the lambda. So in this case, I'll see lambda equal to 2x negative 2x over y. Okay, so let's call this is equation 1, this is equation 2, this is equation 3. Okay. So now once you find the lambda, and then your second step is, well, before you find the second step, here is to sub this lambda into, because I found the lambda from equation 1, right? So I'm going to sub the lambda into equation 2. Okay, into equation 2. The reason is, once I do this step here, so this is basically what's going to be the second step, then you obtain an expression for x and y only. Okay, then you can obtain an expression for x and y only. So let's see what happens, right? If I sub this lambda into equation number 2, then what happens? So I got 2y plus, well, this is negative, but anyway, so 2x over y, this is lambda here, multiplied by x equal to 0. Okay. Any questions? All good? Yeah. So let's look at this one here, and then what happens is, this is 2x plus x, 2x squared, right? And there's 2y plus this, so I guess I can multiply the y, and I'll multiply the y to both sides here, so basically I got what? 2y squared equal to 2x squared. Okay, 2y squared equal to 2x squared. So the two got canceled, you know, right? So you end up with just x squared equal to y squared. Okay. So x squared equal to y squared. Yeah, this is the way when this kind of particular question, you got to be careful. You have to consider all different options, all different possibilities. So for example, here, what are the possibilities? With x squared equal to y squared, that means what? That means x could be equal to y, right? Or what? X is negative y. Okay? Yeah. So that's the two possibilities. Okay. Then you look at the two possibilities here. Which one is the suitable one? Okay. Not all possibilities are suitable. You can actually discard some of these solutions that are here. So let's take a look at this x equal to negative 1. If x equal to negative 1, then when I sub this one into this constraint xy equal to 3, what do I get? I got negative y squared equal to 3, right? Is that possible? No. Right? Negative y squared equal to 3. 3 is positive number, and negative y squared can be positive number, right? Yeah. So this guy here is actually not possible. Okay. Yeah. So x equal to negative y is not possible. Then our only choice left with is x equal to y. So now I got my expression for x, y, right? So basically x equal to y. Okay. So the last step, right? Once we got this x, y here, then we sub this expression into this equation number 3, which is the constraint at here. Okay, the constraint. So step 3. So sub x equal to y into constraint and solve for x and y. Okay, solve for x and y. So let's see what happens at here. My constraint is x, y equal to 3. So you can solve either for x first or solve for y first. Right? So if I solve for x first, I got x squared equal to 3. Right? X squared is 3. So x squared equals 3, meaning x could be what? Right? Positive or negative 3. Okay, positive or negative 3. So that means when your x is square root of 3, you have a y value. When your x is negative square root of 3, you have another y value here. Okay, so that means I got 2 points. One point is root 3, because x equal to y. Okay. And the other point is negative root 3, negative root 3. So that's the 2 points you obtained, okay, based on this condition here. So these 2 points are what do we call it? That's the critical points, right? That's the critical points. And we know that these 2 points basically going to be the minimum points on the surface F. Okay, on the surface F. Is that good? Yeah. So the question, I guess, is to find minimum values, right? Just find the minimum values of this function. So then you need to have one more step here, right? What's the minimum value? So my minimum value here, what you do is you sub this back into this function. Okay. And look at the value of this function f. And that'll be the minimum value at here. So in this case, actually both of them are the same thing. And you end up with a 6 and a 6 at here. So both points, yeah. Yeah, good point. How do I know it's a minimum? I know it's a minimum. Well, in this case, I know it's a minimum by looking at the graph right here. Right? I look at the graph. See, this is my constraint here, right? This is constraint. when you're walking along this constraint here, you end up with basically sort of a grain curves, something like this, right? This curve is not a curve in one plane. This is actually, you can imagine, this is a curve on the bowl, right? On the bowl here, on the surface of the bowl here. Okay, so you look at this curve here. What do you have? You must have a minimum here, right? You won't have a maximum. Is that right? Yeah, because that's the surface that determines this one here. So this kind of surface, if you remember in the last lecture, I called this convex kind of surface here, right? So when you have a convex kind of surface, you guaranteed you have a minimum points when you're walking along certain constraints. Okay? Yeah. Now, but why do I say that's a good question? Because then you should ask another question. What if I have another function f, right? What if I have another function f, and it's different from this one here, and I have no idea whether it's a convex or whatever. I have no idea what kind of surface it looks like, right? How do I know the critical points I find out is a minimum point or a maximum point? Okay, so that's actually a good question. So how do you know that? Then you have to go back to our first lecture. Not the first lecture, sorry. This is lecture 13, right? Lecture 11. In the lecture 11, remember what we did is to find the mean and the minimum of a certain function. Is that right? Yeah. How do we find the mean and the minimum of a certain function? What do? We do a first derivative test, and then what? We did a second derivative test, right? Yeah. Okay. So now the same thing here. So I said the three equation that here is equivalent to which one? To the grading vector of the del W equal to 0. That makes sense, right? That's what I said. So the del W equal to 0 give you the critical point. Basically, this is what? The first derivative test. Right? This is the first derivative test. And the value that you find, the x and y value you find is the minimum of that is basically the minimum of this. Then if I wanted to find whether the x, y value I find is minimum or maximum, I need to do a second derivative test. So the second derivative test basically is a test on this del W here. Okay? And you'll be able to see well. Is that good? Yeah. So some functions are easy, we're not going to be too complicated. In most of the questions here, you probably just say find a minimum or find a maximum. Basically, the question tells you whether the point you're gonna find is a minimum or maximum here. Okay, you don't need to do a second derivative test anymore. Okay, yeah. So, any questions? Yeah. Yeah, this Lagrange multiplier does not stop here. Okay? So if you have a multiple constraints, for example, if you have a function f(x,y) equal to z equal to f(x,y), and then you have maybe two constraints. Okay, maybe you will have two constraints. Now, in this particular case, then what happens is you're going to use two Lagrange multipliers. So you're going to define your W as 2. So C1 plus lambda 2 and T2. So you're going to do this, right? Yeah. So if you have more than that, you could be doing this, right? Yeah. And this is a very useful tool in terms of optimization. And in the control system, optimal control system, this is a fundamental thing you start with. Okay. So then, and you define yourself a performance index. You define yourself a constraint. Okay. Usually, okay, this constraint here, usually this constraint is the system. Okay. The constraint is the system. So let's say you have a mass spin damper system, right? So the system equation maybe is mx double dot plus bx dot plus cx equal to 0. Cx equal to 0. That's the system, right? That's system. So then, non-zero. So let's maybe put an F set here. Okay, put a force set here. Okay, put a force. So then, your x, that's the constraint. Your x cannot be anywhere but be constrained by this ODE at here, right? Or this ODE. Okay. So this is a little bit different from this constraint at here, right? This is a pure sort of scalar function at here, but this is a sort of differential equation as a constraint. Okay? Yeah. Then maybe what you want is, I'm giving a force into this system here, right? Maybe what I want is I want to minimize something. Okay, I want to minimize maybe the energy, or I want to minimize the error of the motion. So let's, for example, I wanted to control the motion of this thing here. Okay, yeah. So then you will have to define yourself a certain objective function f here. So this one here is what user defined. Okay, different user, different industries, you will have a different objective functions. That's why sometimes we call it cost function, sometimes we call it performance index. Right? So this is basically quite useful applications. Okay. Any questions? All good? Yeah. Okay. So now let's talk about a new topic. So we are having partial derivative, basically everything in the function of multivariables. Then we go back to the vector, right? So now we're going to get away from the vector for a temporary. Then we're going to this integral here. Double integral. Okay, so double integral, as you probably can imagine, well, I guess you're going to have two integrals, right? Just like the one integral that you learned, single variables. So double integral must be an integral dealing with function of two variables. But let's start from this simplest case, single function variables. For a function of y equal to fx, so we're going to integrate from a to b. Right? Integrate from a to b. And the way to do this integration, if you remember, okay, so what you can do is you can always use approximations, right? So you can essentially separate this region, okay, into many rectangles, okay, many rectangles. So let's say, for example, at one of the particular rectangle here, so let's say this is one particular rectangle, and I'm going to let these two sides of the rectangle, one is xk minus 1, xk on two sides of this rectangle here. And in the middle of this one here, let's call it the value of the ck. Okay, so in the middle of this xk minus 1 and xk here, let's call it ck here. So this value in the middle of here, so there is a certain function f here, so fck, right? Fck. Okay. So the way we do this integral is you kind of using approximating technique. Okay. So you calculate the area of this one particular rectangle, right? And then you add all the rectangles area together. That will be this approximation, right? Yeah. So the area of one rectangle will be the bottom length multiplied by the height. Right? So the height is fck. The bottom length is xk minus 1. So let's call that delta k, delta xk. So basically total area, right? Total area will be summation of many rectangle areas. One of them is this, right? That's the case number rectangle. So suppose you have any number of rectangles, so your k starting from 1 up to n numbers, right? Up to n numbers. So that's the approximation here. Approximation meaning it's not accurate. However, right? If you let your n goes to infinite, you have an infinite number of rectangles inside this area, then this summation at here turn into an integral, right? This turn into an integral. So this guy turns into an integral, and then it becomes integral a to b fx dx. Okay, fx dx. So that's the idea of doing this single function here, integrals, right? Okay. So now let's extend the idea to two variable function or two variables. Okay. So we're gonna consider this one now. Okay, consider this one. Now before we consider this one here, let's look at this guy here, just a little bit again here, okay? Now When I have a function fx here, and I integrate the function fx from a to b. Now, technically speaking, what happens here is this fx, right, is defined, okay, is defined in this region a to b, right? In this region a to b. So, in other words, you pick any values between a and b, and there will be a value of f of something correspondingly. Okay, right? That's what happens. Yeah. So now, when I have a function of two variables, and corresponding to this simple case here, instead of just a straight a to b, then I must what I would have here is must have a certain kind of region, right? A certain kind of region. Yeah. So instead of saying, this is fx, you see fx defined in this a and b, right? Now in this case here, this function fxy, you see that this function defined within certain region R. Okay, so this is basically indicating by a certain area, right? So this is R here. So this guy is defined, okay, within region. Defined within region R. Okay, so if this is defined within region R, now the thing is, you can think of this fxy as different ways. One simple way is, I'm going to just basically draw the fxy in this 3D space, right? Yeah. So I can just draw it here. So let's say maybe this fxy is something like this, right? That's a surface. Okay, so this is z equal to fxy. Okay. Yeah. Okay. Now, if you don't want to draw it here, right? So that's another situation. Maybe you don't have to draw it. Maybe what you can think of is, maybe this is just some sort of function. Let's say this is a plate, right? This is a plate, and the plate has a temperature, and this function basically represents the temperature within this plate here, right? Within this plate, you pick any points on the plate, you have a temperature, and that temperature is calculated based on this fxy. So in that particular case, you don't really have to draw it out, right? You can just imagine there is a certain value, fxy, associated with any point inside the region R at here. Does that make sense? Yeah. So the reason I'm drawing it out here, I'm basically trying to make use of an analogy here. The analogy is, I have this one here, I have this one here. Now, my point here is, let's try to find the volume between this surface and this region R. Okay, is that okay? So that's basically one of this analogy. Volume. Because I'm using sort of the application of finding volume an example to do this double integral here. Okay. So the whole idea is, let's see, what's the volume between z equal to fxy and region R. Region R here. Okay, so if I look at the volume here, basically that means I'm going to just basically extend this region R and upwards, right? And upwards here. Okay. Then on the top of that, you have a surface z equal to fxy here. Okay, so we're trying to find the volume of that. And if you wanted to compare with this function of single variable here, see, that's the same idea here, right? It's the same idea. See, this function fx is on top of this region A and B, and we're trying to find the area below this fx. And this one here, this function is on top of region R, and we're trying to find this volume, okay, below this function f. Okay? So now the question is, how do I find the volume of this thing here, right? How do I find the volume? Now, in the previous case, what happens is you pick a point here, right? You pick a point inside this A and B, and you use the rectangles to approximate this area. So we can do similar things here. We can do similar. So what we can do is, let's try to pick maybe a rectangle within this region R, okay, rectangle. Then I'm going to extend this rectangle up, okay, extend them up, okay, right, extend it up. Then once your rectangle is up, then you when you hit up the surface F here, you have a certain kind of a box here, right? A rectangular box. Okay, rectangular box. Okay. So if I can find the volume of this rectangular box, and then I can find the volume of the other rectangular box based on other rectangles inside this region R, and then add them up. Okay, I found the volume, right? I found the volume here. Okay, so now first stage, let's find the volume of this rectangular box. Okay, rectangular box meaning it's the bottom area multiplied by the height, right? Multiplied by the height. So if I pick a center point of this inside this rectangular box here, let's see, at this center point here, I'll call it xk, yk. Okay, xk, yk here. Okay. Then I have a certain value, okay, corresponding to this xk, yk. So I have a f xk, yk corresponding to that value there, right? So that's basically the height. That's basically the height of this rectangular box. Then all I need to do is just use this height multiplied by the bottom width, right? Bottom width here. So the rectangular box area is f xk, yk multiplied by the delta area, right? The delta area. So let's see, the delta area is based on this xk, yk, right? It's around this xk, yk at here. So maybe I can call this side of the length is delta xk, and this side of the length is delta yk. Okay, so, oops. So I can call this side is delta xk, and this side is delta yk. Okay. Then this delta ak is basically this. Okay, this. So that's the volume of the one rectangular box, right? Volume one rectangular box. So I guess what you need is you need as many as possible, and then you add them up. So what happens is your total volume is basically going to be a sigma of this, and k from 1 to n. Right? K is 1 to n. Okay. And then similarly, you let n goes to infinite. Right? You let n equals to infinite. Then the summation at here turn into an integral, right? Integrals. So, but the problem here is you've got two variables, x and y. So this integral, instead of just one single integral, so we have two integrals. Okay, two integrals. And the delta turn into small d. So that's basically double integral. Okay, yeah. And a double integral, you can see now, it's a very similar to a single integral. Right? So what are you integrating? You're integrating this guy. So where are you integrating? You're integrating within this region R, right? Just like a single ones, what are you integrating? You're integrating fx. Where are you integrating? You're integrating the region A to B. Okay? So sometimes this one, you can put a subscript right here to represent the region of the integrals. Any questions? Okay. So let me ask you one simple question on here. If this function equal to 1, what does this double integral give you? What does it give you? Area of what? Exactly, of the region R, right? Yeah. So if this one here, you get this guy here, right? Get this. And dx dy, we write dx dy, right? But dx dy basically a small area dA here. Right, it's this. So you can see now, integral of d something, integral of d something, doesn't matter what that something is, integral of d something is always give you, what? The something. So in this case here, that gives you this A here, right? The area, okay? Yeah. Okay, so now the whole question comes to, now you look at this one here, you wonder, how do I carry out this integral here, right? This doesn't give us any clue as how do we compute this double integral here. So this next question is, how to compute this double integral? Okay, so before we talk about how to compute the double integral here, I still want to go back to this single variables here, okay? To these single variables. Maybe I'll redraw it here. Then we're going to use that loaf of bread. So this is a single variable here, right? This single variable, okay? So single variable, when you integrate, this is what you do here. Okay, this is what you do. Now, when you're doing this one here, let's see what happens, right? Let's see what happens. So what happens is, you're integrating from A to B. Basically, it's a concept of sweeping. Okay, it's a sweeping. So you need to cover every corner of the region from A to B. That makes sense, right? Yeah. So it's like this, right? It's like I'm gonna draw a line over here, maybe. Okay, I'm going to draw a line here. Basically, what you do is you let's see if this works. Here's a line here. There's a line here. Then what you do is across this region here, right? You strip this line across the region, right? If you over this region A and B, getting a shaded area underneath fx, which is the area, right? Or which is this integral you're looking at. Okay, so the idea is of sweeping. The idea is you cover every corner, okay, of this integral region. Is that good? Okay. So then back to this double integral here. Double integral. So you want to do the similar thing. So similar thing meaning here's a volume I'm trying to look for, right? Here's a volume. How do I sweep to cover every corner of this R and to give me this volume? It's like a 3D computer. It's like a 3D printer. So how does a 3D printer do? You give the model to it, right? And then trying to fill out all the empty spaces based on the CAD model. Is that right? So once it's finished, you get your concrete 3D model, right? So same thing here. Here's the 3D object, which is basically the surface, this guy, below the surface, this guy, and above this region R. And I wanted to basically cover every corner of that, right? So how do I do the sweep here? When we have the sweeping like what we illustrated here, you draw the rectangle, right? And you draw another rectangle. So you draw as many rectangles as possible. Then you kind of basically stack them up, right? And you end up with this the 3D object, right? Yeah. Okay. So then the whole question here is, if you do that, that seems to be too much work, right? How much rectangle should I pick, right? And how accurate is going to be that approximation, right? So I guess calculation-wise, we're not going to use that technique. So we're going to try different ones here, okay? So the different ones, this one here is this. So let's use this bread here, for example, here. So instead of cutting it into different rectangles here, right? We're gonna slice it. So first thing is, you maybe align this. Move bread properly here. Let's say it's aligned up somewhere like this here, right? Yeah. So you're gonna slice that. So this is a little exaggerated slice. Now I want you to imagine the slice is very, very thin slice. Okay, very, very thin slice. So if you do that, right? If you do that, instead of the previous case of taking all the rectangular box here, then I'm looking for basically now is imagine the top one here, right? This is the surface. Right, this is the surface here. And the bottom one here, that's the region R, right? That's region R. So I'm looking for the volume between the top surface and the bottom surface. So if I use this concept of slice it here, then what I'm going to do? What I'm going to do is I'm going to basically calculate the volume of each slice, right? And then I'm going to add all the volumes up. That make sense? Yeah. So that's basically another way of approximating this, right? This is what we're going to use here, right? This is what we're going to use. Yeah. So if you think of this one here, are you covering every corner? Yes, you are, right? And are you forming this just the 3D object you're trying to aim at? Yes, you are, right? Yeah. So that basically will work. Okay. So now let's look at this idea of slicing it here. Okay. So I'm going to draw this just slightly, okay? Just according to my notations here. So let's see, I have a surface like this. And here is what happens, okay? Here's what happens. Okay, so I'm going to slice it. So I'm going to slice that. So this is one slice I'm looking at, okay? This is one slice I'm looking at. In this particular case, what I'm slicing here is I'm doing this. Okay, watch carefully. I'm doing this. I'm basically this line here. Okay, so this line is parallel to the y-axis at here. Okay, this line is parallel to the y-axis. So this x at here, some kind of value of x at here. Okay, some kind of value x. Is that okay? Yeah. So the bottom is region R. The bottom is region R. So then what happens is, if I look at it into carefully here, there must be a boundary, right, regarding this region R. Okay, it must be a boundary. So there's one sided boundary over here, and then there's another sided boundary over here, right? Another sided boundary over here. So maybe I'll call this sided boundary is x mean, and this sided boundary is x max. Sorry, the other way around. Okay. Yeah. Okay. Yeah. And similarly, for the y, I should have another kind of boundary here, right? And then the boundary. Okay. So this is y max, and this is going to be, yeah, sorry about the drawing here, y mean. Okay. Y mean. Okay, so now to better illustrate this one here, let's just purely look at this slice at here, right? This slice. So I have this slice here. Essentially, that slice is like this surface over here, right? It's like that surface there. So if I look at this slice, okay, project the slice into the z and the y plane, looking like that kind of projection there. So I'm gonna have this is y, this is z. So that slice. It more looks like this one here, right? More looks like this. like that. Is that good? Yeah. So, what about this point and this point here? So these 2 points are basically these 2 points here, right? These 2 points. Right? These 2 points. And these 2 points are on certain kind of region here, right? A certain kind of region here. So I'm going to call, now this, I call this as y, the boundary here, y mean or the y max. But when I look at this slice here, so this side here, there's probably another y mean and a y max is slightly different, okay? Slightly different from that meaning over there, okay? Yeah. So I'm still going to call it y mean, y max. We'll explain it. What's the difference here, okay? Yeah. Still going to call it y mean and y max. And the top one here. Where is that from? That's from the surface, right? That's from the surface here. So the top one here is actually, okay, is that equal to fxy? So you might wonder, how come the curve is this? But remember what happens here. Remember, this is we pick the slice at the location x. So this curve is based on certain value of x at here. Okay, certain value of x. Is that clear? Yeah. Okay. So I have, which is this cross section, and I said I'm gonna calculate the volume of one slice, then add all the slices up. That would be the volume here, right? Okay. But in order to calculate the volume of the one slice, what do I need to do? I need to calculate this area first. Then multiply by what? By the thickness. Yeah. Yeah. So good. So then let's see, volume of one slice equal to the area of the slice multiplied by thickness. Okay, multiplied by thickness. Okay, remember what we did? Where we did it? We did a slice at the location x at here, right? This slice at location x at here. Okay, so now this is the cross section of that slice, or the area of the slice. Then, in order to get the area, what do? We integrate, right? We integrate. So basically, this is the integration. Now, where are we integrating? We're integrating from this side to the other side here, right? So that'll be basically y mean to y max. Okay, y mean to y max. Okay. So we'll look at what exactly is y mean, y max here, but for the so where are we integrating? We're integrating this function, right? This function. And what's this function? That function is fxy, right? fxy. So integrating this guy here. What variable are you integrating? You're integrating along this axis here. So you're integrating which variable? You're integrating y. So dy at here. Okay? dy. So in other words, when you do this integration, you're going to consider the x as a constant, right? Yeah. Then multiply by the thickness. So thickness meaning the thickness of this slice here, and we're talking about very, very thin slice. So the thickness should be dx. Right? Should be dx. Okay? So that's the volume of one slice, right? Volume of one slice. Okay? But what truly you need is the volume of the whole bread. So volume of the whole thing. Then volume of the whole thing meaning you're gonna add this volume everywhere up, right? Add them up. Add them up meaning you are basically doing another integral again, right? Another integral. So in this time, you're adding them up. This time you're adding from this direction to this direction. In my case, I'm gonna add from where? From here to here, right? From here to here. So basically, you're gonna integrate from this x mean to x max. So basically, just integrate this whole chunk. So I use big bracket here. So that's what happens here. Okay. So this way, you covered all the corner, and you're able to form the solid, okay, which is below the surface above the region R. Okay. So you're not going to miss any possible locations. Okay. So that's essentially how you calculate double integral. Okay. How you calculate double integral. So you look at this calculated double integral here. It seems to be very simple now. All you need is what? Do two integrals, right? First integral is integrating with respect to y, and the other integral is integral with respect to x. The only tricky thing now is what will be the integral limits for each one of them. Right? That's basically the idea now, right? Yeah. The thing now is finding the limits. Okay, finding the limits. Okay. So finding the limits, you have to understand the limits that are here. What does it refer to, right? The limits that are here refer to what? To the region R. To the region R. So essentially, we need to focus on the region R. So let's see, I'm going to single out the region R here. This is XY plane. Region R is XY plane. So I'm going to draw the region R somehow like this, okay? So this is my region R here. Okay, this is my region R. And we're trying to figure out the limits. Right? We're trying to figure out the limits. So region R meaning it can be anything, right? It can be anything here. Now let's start with the simple case, right? More of a general but still a simple case. So suppose this is the region R is consisted by maybe 4 simple curves. Okay, 4 simple curves. There's a top curve here. There's a bottom curve here. Okay, yeah. Then when I'm talking about curve, basically we're looking at its xy plane. So the top curve and the bottom curve, I can express them as certain kind of functions, right? So maybe I will express the top function as y2 equal to maybe f1x or f2x, and the bottom one maybe y1 equal to f1x. Is that possible? Right? That's possible. Okay. And now we go back to how we do this slicing, right? How we realize the slicing here. So how do we do the slicing? We pick a point between this boundary here, somewhere in between. Then we slice that region R, right? Like this. Okay, we slice it like that. So then what happens is you slice like that, then you integrate from one side to the other side, right? You integrate from one side to the other side. And we call that one limit is y mean, and the other limit is y max. Make sense, right? So now if I look at this one here, you need to imagine that surface on top of it, right? And surface on top of it, so you have a slice. When you're integrating from here to here, right? Integrating from here to here. So if I define this as y1, this is y2. So guess what? What will be the y mean and y max now? So you're integrating from here to here. This is A to B, right? This is A to B. So what would be this A to B now? That's right, f1, f2. Because you pick a point x arbitrarily between this boundary here. So if you think that anywhere here, anywhere along this mean or max is always being expressed by y1 and y2. Right, f1 and f2. Okay? Yeah. So that's the integration of this slice, right? That's the integration of this slice here. Okay, that's integrating this slice. Okay. Yeah. And then the next step is, here's when you find the volume, the whole thing is what? You're going to basically, you're going to sweep this slice, right? Basically, you're sweeping this slice kind of back and forth to cover the whole solid, right? To cover the whole solid. So when you're going back and forth, covering the whole solid, you're essentially going from x min to x max, right? And this time, when you go from x min, x max, that has to be what? That has to be exactly the edge of this region R, right? From one edge to the other edge. So then, if I look at my region R here, this time, edge meaning not a function anymore, meaning it's going to be what? Is that exactly? It's going to be a certain constant at this side and at this side here. Okay, and this and this side. So now that gives us the integral limits for this double integral. Okay, for double integral. So for this particular case, what I guess is, let's say this is x min, maybe I don't know, maybe certain values. Let's just take this x min, x max, and that y min basically becomes f1x, f2x. Okay, and then integrating this function xy, dy first, and dx. Right, so that's how you find. So this x and x max, okay, they are constants. Okay, they're constants. Those are constants depending on the region R. Okay, those are absolute edge. Okay, absolute edge. So this region R here is a very simple region. If you have a relatively more complicated region, that's what we're going to talk about next. Okay, in later lectures. Is that clear? Yeah. So double integral actually is quite easy now. Okay, all you need is look at the R carefully and find, okay, the limits. Okay, find the limits. Before we move on here, and I think we can still think of one thing here. Okay. So the way I did a slice it here is what? I slice that along this y-axis, right? Along this x-axis. Basically, I choose x location and do a slice, right? Yeah. So I think the natural answer to the question is, can I do a slice like this? Right? Absolutely. Absolutely. So if you do that, then what happens is the integral order will change. Instead of a dy first, you're going to do this dx and then dy. Okay? Yeah. Then the mean max, right, should also be changed accordingly. Is that correct? Okay. Good. Now let's look at a simple question here. Okay, good. Yeah, next time you have a loaf of bread, you can try to capture the volume, but just don't be too accurate. I have a plane. Okay, 4 minus x minus y. So let's start. So let's say suppose it's a plane here, okay? And we're going to have a region R, which is a very simple region. Okay, here's region R. Where x is between 0 and 2. And y is between 0 and 1. Okay, so you're looking at sort of a box here, right? But it's not a regular box. So we're trying to find volume. Okay, let's find volume here. Okay, this is very simple here. So here is the formula for calculating the double integral, right? Okay, yeah. So let's see which we shall we do, and are they going to give us the same thing? Okay. So good, all right. So let's take a look at this one here. So I'm gonna maybe still try this formula here, basically, which means I'm gonna do this dy first and dx. Okay, integrating out of y first and then x. So if I do that, so that means what I'm gonna do is I'm gonna find a location, okay, between 0 and 2, right? That's the x limits, and then I'm gonna do a slice, okay, like this, right? I'm gonna do a slice like that. Then you can look at the corresponding cross section, which is more or less like that. Yeah. Okay, so this is the cross section, and then we're gonna basically sweep this cross section back and forth to form the solid, okay, or to get the volume. So that's actually quite simple. If I look at from top view here, right? Top view. My region R is basically a rectangle here, right? It's basically a rectangle. Then we are slicing somewhere between, from here to here. Then sweep this line across this region R, okay, to cover all the corners. Okay. So then the whole question basically is to find the integral limits. Okay, so this is your formula for calculating volume. And in our case, we need to figure out this integral limits. Since I'm doing this y, so I'll just write it down first, right? And then figure out the limits. So y meaning you're doing this way here. So what's the limits now? So now you're cutting it anywhere between 0 and 2. Because the simple region R, doesn't matter where you cut. The y mean and the y max is always 0 to where? 1, right? It's always 0 to 1. Okay? Yeah. And then you're sweeping this line here. Basically, the second integral, you're sweeping this line or the slice, okay? And to cover from one edge to the other edge, right, of the region R. And that one edge is give you x mean, the other edge give you x max. So in this particular case, it's 0 to 2. Is that right? Yeah. Okay. So fxy is given by the surface z, which is this function. So we just plug in. Yeah, just a second. Okay. Yeah. Oh, this limit is for x. Oh, sorry. Where did I draw you? This is. Yeah. Is that it? Yeah. Oh, if I draw the y here, actually, it doesn't make sense. I don't have that kind of coordinate system. Yeah. Now let's look the back on the computer, that side there. Okay. Yeah. Sorry about that. So now the whole thing left is just the integral. Okay. When you do this inner integral, you treat x as a constant. Okay. You treat x as a constant. So do it carefully. Basically, you got 4y minus xy minus 1/2 y squared 0 to 1 dx. Okay, dx. Okay, so plugging all the numbers. Okay, plugging all the numbers. So you get 4 minus x minus 1/2. Okay. Okay, so then here's 4 minus 1/2 is 7 over 2. 7 over 2 x minus 1/2 x squared. 0 to 2. Okay, 0 to 2. So sub the values in it, you got 5. Okay, got 5. Okay? Yeah. So this is the order of integration from dy first, then dx, right? Then dx. Okay. You can try the dx first, then dy, and then you should get the same thing, right? You should get the same thing. Okay. Now this is a very simple thing here, very simple here. This actually, I don't even want to bother to write it down here. In a textbook, you call it they call it Fubini theory. Basically, when the region R is a rectangular region, okay, then your limits here basically is the limits of the rectangular region. That's called Fubini theory. But you don't really have to remember that. Just remember the general case here. How would you find the mean and max? Okay. Yeah. Any questions? Yeah. And yeah, I think I'm gonna save the rest for the next lecture. Yeah.